Ladies and gents, welcome to a first in a series of recordings that will continue our journey in earth science. As suggested in the announcement that I put at the top of Canvas, you have the option to watch recorded lessons. Here they are. This is one of them. Or tune in live for actual lessons being delivered from the classroom from now probably until the end of the school year. Every day, Monday through Thursday, or in this recording's case, obviously Friday will be included, to tune in at 9 o'clock, okay? Every day, 9 o'clock every day for your earth science lesson, okay? So you have that option to watch it in progress, and you also have the option to watch the recordings at your leisure. So here we go. We're going to dive right in with today's topic, the Big Bang. Specifically, how did it all begin? That's our governing question. How did the whole universe begin? And more importantly, how do we know that the Big Bang is an accurate depiction of how it all began? There's 4 key lines of evidence. You're going to be taking some notes today, so have a piece of paper and a pencil ready. Don't start writing stuff down just yet. I'll cue you for that, and I'll show you exactly what to write down at that time. And we'll do a few simple sketches and make sure that it's clear to you what's really important when you want to understand the mechanics and the proofs behind the Big Bang Theory. So, how did it all begin? It started with a Big Bang. No, look at what you can see in this picture. Take a look for a moment. Kind of glance around at the different features captured in this composite. It's several different images spliced together. Beautiful rendition. Not exactly accurate, but it is a beautiful rendition of a certain part of the universe we can see with our telescopes. What do you see in this picture? Hopefully stars jumped out at you right away. The brightest objects, the little pinpoints of light with the little, star spikes, because of camera lenses, create those spikes of light. Okay, good. So you got stars. Now, look for galaxies. Look right straight, basically up above my picture here, right up there, and you'll see this fuzzy kind of disk image. That's a whole galaxy right there in that particular picture. And then look in the middle of the picture, there's a pinkish glowing orb. That's another galaxy. So we've got whole galaxies within the range of this particular composite. Clouds of gas in space. Can you think of the name for a cloud of gas in space? And if you said nebula, you'd be right. Now think of this, my Spanish speakers, se habla español. The word for clouds, right? And if you're thinking, I know, nubis. Yes, nubis, and the Italian word nebbia, these are Latin roots for the word cloud. Where do you think we got the word nebula from? Nubis, nebbia, nebula. There you go. Okay, a cloud in space. Dust particles, gases, and small fines just floating in space, waiting to congeal together to make new stars and to make a galaxy a growing entity in space where it's growing new stars. But how did all this begin? Let's take a look at the Big Bang, a closer look. At first, there was nothing at all. A point, impossibly small, unimaginably dense. We don't even have numbers to describe how dense it was. We can't even fathom how many trillions upon trillions of degrees the temperature must have been right at the instant it began. But we know what happened next. There were no stars at first. There were no planets, just one huge cloud. After a burst, and that cloud got bigger and bigger in all directions as the universe started small and just grew bigger and bigger in all directions. Very quickly, the universe was bigger than our solar system, bigger than a galaxy, and yet not a single star shined. No planets yet were around to walk on. No life, nothing but the element hydrogen in huge abundance with a tiny little bit of helium and a trace of lithium sprinkled into the mix. Just the simplest elements, and the first stars had not even formed. But eventually, pockets within this expanding gas cloud settled down and began to coalesce and swirl, and gravity started pulling them together in denser and denser pockets. And as these clouds shifted and moved within each other and combined together to make heavier zones more dense, they started building stars. Gaps in the universe started opening up. Light started to shine with the birth of those first stars. And as those clouds in space began to create stars, the first giant blue and normal yellow stars started to be created. Even some small little red dwarfs began to be born out of these clouds, and they would migrate out from the clouds where they were born, and the first small galaxies began to form. So that's kind of the process of what happened, based on all the evidence that we've gathered, all the information, all the data, observations, mathematics. Everything tells us this is the way the universe came to be. But again, that doesn't exactly answer how do we know. The last thing I want you to do is say, trust me, this is how it was. Let's talk about why. Why do we know for sure this actually happened? All right, so at this time, have that piece of paper handy. Let's build some Cornell Notes to answer this question. How do we know how it all began? So my note takers at home who haven't been in class before, whenever you see this little green icon, the hand holding the pencil, that tells you, ooh, something on this page is something I should write down. And in this case, everything in green. Make sure you write it down. So for your Cornell Notes or your blank piece of paper, please begin at the top. Write down your name, you know your name, the class, earth science, whatever period you're assigned to, okay, and the date that you're taking these notes down. Please write those things down. Your topic today, the Big Bang Theory, sure enough. Your essential question, one of the most important blanks on your Cornell Notes is your essential question. Today, how did it all begin? You could even add, if you felt like it, how do we know? So pause it here. I'm going to dive straight in, but pause it here until you have all of those things written down, and continue when you are ready. All right, so let's dive into what we know. Here's what I would like you to do first. So on your paper, in the section where you take your notes, leave a little space off to the left to ask questions later. But for now, your main notes section, put 4 boxes going down your page and do little simple sketches inside those boxes. Next to each of the boxes, write down these titles. These are your 4 proofs of the Big Bang. I'd like you to take a moment. In the top one, sketch a microwave oven. Yes, the kind that you use, excuse me, the kind that you use to nuke a bowl of soup or some popcorn. So sketch a microwave. Then in the second box, put 2 H's coming together to make an HE. The third box, put a galaxy up in one corner, a simple little swirl of a galaxy, and another one down in the other corner, leaving a clear gap between them. And the last one, put that cloud we saw in the animation a moment ago. Put a cloud and arrows showing it expanding in all the directions simultaneously. Okay? That's your setup for understanding these things. The words in green, put them next to each of your boxes, please, but leave a line underneath so you can add what it is. Okay, so you can leave a space to add a few words underneath 1, 2, 3, and 4. Again, pause it here because I'm going to continue forward. Pause it until you've created these drawings and written down all the 4 different titles, if you will, of the proofs of the Big Bang. Pause me here as you need to. All right, let's consider number 1, the cosmic microwave background. I'm going to start with a little story about it, and then we'll get into what it really means. Imagine this. You've got, in your house, there's a fridge where the food is kept, and on the fridge is a picture of you as a baby in a bathtub. And you're splashing around and you're adorable and you're the cutest little thing ever. You're just the most adorable baby. And your mom has a Polaroid picture or some other printed picture, and she put it on the fridge, and you hate that picture of you as a baby, cute, little, chubby, and naked, sitting in your bathtub, and you would just love for that picture to go away, like be gone. You want to do like make that thing vanish. And your mom knows this. She's like, don't you touch that picture, or you'll be doing dishes until you're 30. And you're not a fan of dishes, so you don't want to do dishes until you're 30. So the picture just stays up on the fridge. That picture of you as a baby, it's there on the fridge forever. And there's nothing you can do about it. That picture will never change, and it will never go away. Ironically, that picture of you as a baby on the fridge that your mom refuses to take down is the first line of evidence for the universe. The cosmic microwave background, my friends, is the universe's baby picture. So next to your microwave icon, you wrote cosmic microwave background. I would like you to add the words in green. Don't worry about writing this entire paragraph from the Planck Institute. Gee whiz, there's really smart people there at the Planck Institute. Capture the green words from their definition of what is this CMB. It is the oldest light in the universe, imprinted on the sky when the universe was a baby. Compared to how old it is now, 380,000 years old, that's when the light was captured, just like a Polaroid. It's in the night sky all the time, and there's nothing we can do about it. That image of the universe as a baby will never change. Okay, it's always there. So capture those details. It's the oldest light in our universe, imprinted on the sky. And you might want to add, my suggestion, the universe's baby picture is the CMB. Now, I'm going to show you what that picture looks like. It's going to seem a little strange. And then I'll show you how they took the picture and why it looks the way it does. So, first, what does it look like? It was taken by this very strange-looking telescope. They discovered it completely by accident. There's a whole separate story there about how Penzias and Wilson in 1965 started piecing together what they thought was just noise in the universe. What they didn't realize was it's an actual baby picture. And what it looks like, there you are. There's the Polaroid of the universe as a baby. You're so cute, this little universe. I just want to pinch his little chubby cheeks. You're so adorable, you little baby universe. That's the entire universe, my friends, in one photograph. Remember, at the beginning, no stars, right? No suns, no galaxies, no planets. At the beginning, it was just a gas cloud. And that heat of the initial instant slowly cooling off. That heat produced a radiation. Part of it was infrared, like what we understand as heat. Part of it was microwaves. So that picture you drew of a microwave oven, there's a reason you did that. That kind of light that we use to heat our food is the kind of light, basically the same bandwidth of light, that this universe's baby picture exists in the night sky. Okay? So, every night you go outside, you look up in the sky, this thing is not what you see, right? Obviously, you see darkness and points of light and occasional planets and whatever, comets, shooting stars, the moon. If we could see in something other than Roy G. Biv, right, the rainbow colors, if we could see beyond those, we'd see infrared, we'd see ultraviolet, we'd have like night vision. If we could see microwaves, the way our machines can see them, if we could see them, this right here is what the universe would look, what the night sky would look like every night, our entire lives. The picture would never change. If we could see microwaves, my friends, Somebody be like, hey, you guys, we're going to watch this movie. I'm going to put on some popcorn. And somebody else would be like, whoa, 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 wait, don't push play. Don't start that popcorn just yet. And we would pause our movies to go in and watch the microwave oven cooking the popcorn. We'd lean up close to the glass and go, whoa, it's so pretty. Look at the microwave. It's so beautiful. But we can't see that kind of light, can we? We see Roy G. Biv. We see the rainbow. If we could see microwaves, this would be the night sky we can see. Okay, but our eyes just don't work that way. So now, why does it look like a stretched out robin's egg? Pretty colors, right? Oh, it's so beautiful, psychedelic, right? Okay, let's talk about why this picture looks the way it does. Remember that crazy looking telescope? They pointed it. Look how it can rotate and swivel and turn and look up, look over, turn around, and kind of look at the entire sky. It wasn't until we had a satellite up in orbit that was looking around the Earth in all directions. It would paint a strip of the sky, and then another one, and then another one, and then another one. And pretty soon it had a spherical view of the entire universe. Okay? Splice all those little painted stripes together, and it has this. Take a look at how it actually gathered that information. Check it out. So it looks in all directions, and it's scanning the sky for those microwaves and puts that image together and then stretches the image out flat. One composite stretches it out flat, and we get this cool, oval-looking robin's egg thing produced by our very best technology, looking for the cosmic microwave background, the universe's baby picture. There you go. That's how the Polaroid picture, if you will, that's how it was taken, the baby picture of the universe. Now, they've had a much better scan of the universe from the original, this is the one from like the 1980s, okay? And then with better technology, we've got a better image of it now. So this image became that. Check it out. High resolution image produced by, again, the Planck Institute, and they spliced together high resolution images of the universe's baby picture in as high a resolution as we can manage with our technology now. Again, the entire universe in one photograph. Now, gee whiz, Sandrock, you showed us a cool picture of the night sky that we can't see because it's not the kind of light we can see. How does that prove the Big Bang? Let me suggest this to you. If someone who had never, imagine some creature, intelligent, had never seen a human before, and they meet you, and they're like, oh, look at you, you're 5'5", you're 120 pounds or 130 pounds or whatever, and you are tall and you have this color hair and that kind of, you got 2 arms and 2 legs. This must be how you've been forever. This is who you are. You've always been this way, right? Always. And then they look over your shoulder and they see the baby picture of you on the fridge. And then they realize, whoa, okay, so if that baby picture is you, and you are now much taller, your body has developed in a way that you don't even resemble a baby anymore. You're still human. But that person, that other being, can look at you now and say, they're a teenager now, they were a baby then, there must have been a point right before they were a baby that they were born, that they began living. You haven't been exactly as you are now forever. You had a beginning time point where you didn't exist before that, but now at that time on your birthday, you did start existing. And here you are growing and changing. That's the universe, my friends. If you have a baby picture of the universe, this one right here, right? Then we know it must have had a beginning. If it had a early point in its development, it must have had a beginning right before that. Logically, it makes perfect sense, and they've determined that this is exactly the case. Okay, so that's number 1. That's the longest description of all of these you're going to get. The remaining 3 we're going to jam through very quickly. Let's take a look at number 2. Hydrogen and helium. I'm going to move my little picture. Hydrogen and helium are kind of important considerations because if we measure how the universe has turned its hydrogen into helium in the fiery hearts of the stars, right? So hydrogen, take one little hydrogen and another little hydrogen, right? And in the core of our sun and all the stars, they're jamming them together and saying, I know you don't want to be together, but boom, now you make helium. Fusion, right? Hydrogen, helium, and lots of energy is released. Mathematically, hydrogen turning into helium happens at a predictable rate. It's almost like your car driving down the road, and you know you've got like 400 miles of worth of gas in the gas tank. And you drive for a while, and you drive for a couple hours, and you think, I should probably be close to half a tank. And you look down at the gauge, and you're like, oh, cool, half a tank. So much time has passed at driving at interstate speeds, you should be at half a tank. You look down, you're at half a tank. That's what this right here tells us. The universe is not at half a tank. It's still got plenty of time left to go. But we can measure how long we've been on the road by looking at our gas gauge. We can measure how long the universe has been around by looking at how it changes its fuel, hydrogen. And here's the cool thing. The measurements predicted by the Big Bang match what we observe, what we can count. We use light coming from all directions to measure how much hydrogen is in the universe. And they match to more than 10 orders of magnitude accuracy. They fit the Big Bang basically perfectly. And how often does something in science or in nature match what you expect perfectly? You look down at your gas gauge and you expect, I should be half done with my tank. You look down like, boom, yeah, oh, cool. I was exactly right. Half gone with my tank of gas. So, abundance of the elements. The universe started 99.9999999% hydrogen. Now it's at about 73% hydrogen. That's what's left in the universe. And it's converting it slowly into helium over billions of years. So, number 2. Abundance of elements, capture the green for your notes if you will. Almost all hydrogen at first, and the other elements formed later inside stars. All the elements in the universe, my friends. The carbon in your muscles, the calcium in your bones, the oxygen you breathe, the iron that carries the oxygen in your bloodstream to your muscles and to your brain, the iron in your blood. All of those elements were created in the stars. And we can measure how long it's been. That's where H and H, you see the picture way the heck over there on the other side, right? The picture you drew, H, 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 E. That's hydrogen and hydrogen coming together to make helium. There you go. Okay, pause this if you need to, capture your notes. I'm going to move on to number 3. Here we go. Number 3, the gaps. The universe has gaps, not just between the stars. There's like light years of space between stars. But the universe has huge empty spaces between the stars and the galaxies. If there was a Big Bang and everything was all together in one point, all the stuff in the universe in one tiny point, and then it was unleashed and grew in all directions, eventually there'd be gaps and spaces everywhere throughout the universe as those little clumps of this universe started moving apart from each other and opening up. Almost like all of us gather together on a football field behind Granger High School, and we're like, all right, ready, break, and we all scatter in opposite directions. We are expanding as a group. There's lots of gaps between us, and every one of us is moving away from all the others of us. That's the universe, my friends. Universe, the Big Bang Theory predicts gaps between stars and galaxies, and there are. The gaps can be huge, hundreds of thousands of light years, millions of light years. And a light year is a huge distance, as you can see by the gee whiz trivia bit there. 6 trillion miles. All right. That's number 3. I said we go through these quickly. Again, pause if you need to. Number 4. Number 4, the expansion, the movement. Not just there's gaps in the universe, but how it moves. Light tells us we could see how things move based on the shifting in the light. It's called the Doppler effect. It's easy to measure once we know it's there and have the right kind of equipment to measure it. The Doppler effect shows us that the stars are all shifting and moving, but more importantly, all the galaxies are flying away from us in all directions ridiculously fast. Like, I'm talking screaming apart, flying away at a fraction of the speed of light. That's fast. For a whole galaxy to be shifting away from the other one, occasionally they do come together or pass near each other. That's gravity. But in general, almost everything in the universe is flying apart from almost everything else. So if you were to lean back from the universe, grab your remote control, right, and click pause on the universe, and then hit the rewind button, instead of flying apart, things would start coming back together again, and together, and then boom, they all come together in one tiny point. If you rewind it, the universe back 13.8 billion years, it would all be in one impossibly small point. Super dense, really hot, the Big Bang. So the expansion of the universe logically proves to us once again the fourth line of evidence. The universe began with a Big Bang. All right? So capture the green for your notes, please. Make sure you don't miss anything in green. Make sure that's part of your notes. Okay. All right. So the last thing I would like you to add, that number I've mentioned a couple times in the video, 13.8 billion years old. That's the age of the universe. That's just something worth knowing. It's such a fascinating and interesting fact. Let's hang on to it. Lock it in your brain. How old is this? The Earth? 4.5 billion years, 4.6 billion years. How old is the entire universe? Quite a bit older, 13.8 billion years old. Before that, we just don't know, and science has no business commenting until we can figure it out scientifically. Before that, there's nothing we can prove. We can only go back to T equals 0. That's the Big Bang. Okay? All right, from this point, I would like you to take just a couple minutes, make your Cornell Notes work for you. Write down 4 questions, 1 for each of the blocks. Write down a question that your notes give you the answer. Now you're thinking like a teacher. Now you're thinking like a college professor. Because if you can ask a challenging question that you have the answer to, you're in essence creating your own knowledge check, your own quiz, your own test. And if you can do that, you have mastered what it is you're studying. Okay? So 4 questions, 1 for each block that you created. 2 sentences at the bottom. Your sentences could be something like, today we learned there's 4 different proofs of the Big Bang Theory. They are cosmic microwave background, the abundance of helium and light elements in the universe, the gaps in space, and the expanding universe getting bigger over time. Boom. That's 2 very information-filled sentences that capture what we talked about today. Okay? But make them your own. Your sentences, your choice. All right? So, thus ends our discussion of the Big Bang. Okay? Our look at the evidence of how it all began. All right? Thank you for tuning in and watching. Keep those Cornell Notes. They will come in handy as we move towards our next assessment, as you show that you have mastered the ideas and the concepts, the most important understanding of how the entire universe began. It's a pretty big deal, literally and figuratively. Thanks for watching, and keep tuning in. 9 o'clock every day will be classes available to you if you want to watch it live. In fact, I'll start up here shortly for our 9 o'clock broadcast every single day from now until the end of the school year, Monday through Friday, 9 o'clock. Look in Canvas for the links. Check your announcements. Stay caught up on all your classes. You're going to own this crazy mixed up year. You're going to do fine. Just stay with it. Don't fall behind. All right. Let us know how we can help, and thanks for watching.